Okay, question 8. This is our last question on the foundation paper. So this question is about radioactive decay. It says, figure 1 shows the label from a box containing radium-226. That 226 is its mass number. What that means is on the periodic table, you would have radium, and you'd have a number which is 226, and you'd have a number underneath, and that's the atomic number. And this one here is the number of protons plus neutrons, which is the mass number. The atomic number is just your protons. So radium-226 emits alpha, beta, and gamma radiation. Figure 2 shows the activity of radium-226 will change. So this is a half-life graph, and it says determine the half-life of radium-226. So half-life graphs are normally dead straightforward. Like with any graphs, the thing that we need to do before we do anything is we need to figure out the scale that the graph is using. So to do the scale, we are interested in here. We're interested in this bit. So I'll zoom out. And what I mean is we need to figure out how many squares make up a certain number on our y-axis. So we've got 1, 2, 3, 4, 5 squares here. So we've got 5 squares is equal to, we've got a difference of, each 5 squares is a difference between 0 and 20,000. We can see that next one. So the next 5 squares, we've got another 20,000 increase, and then we've got another 20,000 increase, another 20,000 increase. Yep, so each 5 squares is worth 20,000. Oh, 20,000. So let's, 20,000 becquerel. I just lost a 0 there, so 20,000 becquerel. So let's figure out what 1 square is worth. So what I did to get to 5 to 1 is I divided by 5, so we do the same thing over here. So do 20,000 divided by 5. So 20, last question, 20,000 divided by 5. So each square is worth 4,000. So 1 square is worth 4,000 becquerel. Now, you don't need to do that, if that's not going to actually help you get the, that's not going to be on the mark scheme, that is need to be done. But in order to understand graphs, I think it's really important that we know how to work out what every single square is worth. I'll show you why we need that now. So you can see here, if I zoom it in, that this first reading is 1 square above the 180,000. And if we know that each square is worth 4,000, we know that this number here is 184,000, 184,000, because it's 4,000. Each square is 4,000. So our starting value is 184,000. Now, what half-life means is it's the amount of time it takes for the starting value of radioactive particles or activity to half. So what would be 1 half-life? We'll divide it by 2. We half it. So let's get our calculator. Let's half that. 184,000 divided by 2 gives us 92000. So that is, we will have our first half-life when our reading is down to 92,000. So what we need to do in our graph is we need to find 92,000. And we know that each square is worth 4,000. So we go to our closest ones, we've got 80,000. So that's 84,000. 88,000. 92,000. So 92,000 is this square here. So what we do is we draw a line very carefully until we hit the graph there. And then what we do is we draw a line down very carefully again along that same line till we hit the bottom one. Whatever this number is on the y-axis, our time in years, is our half-life. That is the time it takes to half. So again, we've just got to figure out that scale. So this time, just going to rub this out. This time we've got 10 squares. 4, 5, 6, 7, 8, 9, 10 squares. So 10 squares is equal to 1,000. So every 10 squares, it goes up by 1,000. So what's 1 square worth? Well, we divided that by 10 to get to that, so we're going to divide this by 10. So let's do that. 1,000 divided by 10. You might be able to do that in your head, but even still, I would use a calculator on exam day. 1,000 divided by 10 gives us 100. So each square is worth 100 years. So we've got 1,000. Again, I'll just rub this out. We've got 1,000 here. We've got 1 square. 1,100, 1,200, 1,300, 400, 500, 600. So our answer is that one there, which is 1600. So our half-life is 1,600 years. Radium-226 was discovered by Marie Curie in 1898. The notebooks she used were contaminated with radium-226 and are still hazardous. Explain. So we've got to give a reason why. Why the notebooks are still hazardous. Well, what that means is that, let's think about it. So the half-life of radium-226 is 1,600 years. So it would take, from her using it until the radiation becoming half, would be 1,600 years. It hasn't been 1,600 years. So the radiation is still going to be pretty high. So let's figure out how many years it actually was. So if we look at the current date, so we're currently in 2022, and if we take away 1898, which is when she was using them, let's figure out how many years ago that was. So 2022 minus 1898, so that was 124 years. So 124 years ago. So the half-life for radium 226 is 1600 years. Excuse the spelling there. If you get there in the exam, just cross it out. Years. But only 124 years have passed. So the sample will not have decreased its activity by very much. So it will still be hazardous today. Okay. C, and this is the last thing we have to do on the paper. It is worth for 6 marks. So it's another long answer question, so we need to have a plan. Explain, again, so we have to say why. Explain how the properties of alpha, beta, and gamma radiation affect the level of hazard at different distances. So we've got to talk about the distances of alpha, beta, and gamma. So we're going to mention each one, and we have to talk about the hazard at a distance. And we're just using this to check off, and we can say when we've done it. Okay, so let's start with what we know. So we know that the alpha. There's a diagram that you probably would have seen where you see this alpha, beta. I should use the proper symbol for beta and gamma, and you are showing the alpha particle, and you're showing a piece of paper. So we start with paper here, and the alpha is stopped by the paper. The next one is aluminium. Here, and we show that the alpha doesn't even get through the aluminium, and the beta goes through the paper, but is stopped by the aluminium. And then we have lead. All right, and we see that the gamma goes all the way through those, and is eventually stopped by the lead, even though some may get through. And this is what we talk about penetrating. So how far they can travel before they are stopped. Now, there's nothing in this question that said there's anything in the way. So actually we think about how far they can travel in air. But it's the same idea that the alpha particle can travel the least far in air. It's easily stopped because just like it's been stopped by paper, there's gas in the air and it can only get through so much of the gas before it's stopped. So we can say that uh, alpha is the least penetrating. You can see that it's stopped by the paper. So alpha is the least penetrating of the three types of decay. It can only travel a short range in air. However, it is the most ionizing. So what ionizing means is that it's like, what are the chances of it removing electrons from cells? And if it removes an electron from a cell, it'll turn the atoms in those cells into ions, which can cause a mutation. And then when the cells copy, they copy with the mutation. And then that mutation could possibly lead to cancer. So alpha is the least penetrating, but it is the most ionizing. So it is the most dangerous at very short distances. So I have talked about my hazard of distance of alpha. I said it's least penetrating, but it's the most ionizing, and it can only travel very short distances. So hazard distance. Let's talk about beta. So beta is moderately penetrating. So it can go through the paper, and it'll go a fair distance in air, but not as far as gamma. So it's big. It was moderately penetrating. It can travel further in air than alpha, but not as far as gamma. It is moderately ionizing, so it will not remove electrons as easily as the alpha will because it's a smaller particle, but it will remove it more easily than the gamma will. So it's more dangerous than gamma. So beta is moderately penetrating. It can travel further than alpha, but not as far as gamma. It's moderately ionizing, so is the most dangerous at medium distances. If like distances where the alpha would have not been able to penetrate to, but the aluminium, the beta would, and the gamma would. So I mentioned the beta. Now we're talking about the gamma. So gamma is the most penetrating. It can travel long distances, and you should remember this, several kilometers in air, but is the least ionizing of the three types of decay. It is therefore the most dangerous at long distances. not as dangerous as alpha or beta over short distances. All right, so I have talked about the hazards as a distance for each one. I have mentioned the penetrating power of alpha, beta, and gamma. I've also mentioned the ionizing power. All I need to do is read it back, and have I answered my question? So, alpha is the least penetrating of the three types of decay. It can travel a short range in air. However, it is the most ionizing. It is therefore the most. So it is the most dangerous at very short distances. Does that answer this? Explain how the properties of alpha, beta, and gamma. So the properties we talked about: penetrating and ionizing. And they're the only properties you're meant to know. Affect the level of hazard, so how dangerous they are. So we say it's the most dangerous at short distances. Yes, that answers that. Beta is moderately penetrating. It can travel further in air than alpha, but not as far as gamma. It is moderately ionizing, so it's the most dangerous at medium distances. Yep. And gamma is the most penetrating. It can travel long distances, several kilometers in the air, but is least ionized of the three types of decay. Is therefore spelling, the most dangerous at long distances, but not as dangerous as alpha beta over shorter distances. Okay, I think that answer there matches up very closely with what I've been asked to do, and therefore I'm going to end my paper there. Hopefully that has helped you out, and you're a little bit more confident with some of those key topics that are going to be asked on the physics paper 1. All right, thank you for watching.